Hello and welcome to another GCSE tricky questions for maths. Looking at grade 9 this time, specifically proof. There's going to be two in this video today, one with circle theorems and one is an algebraic one. So just two different examples of something that comes up quite regularly. Okay, so we can clearly see this question is about circle theorems. We've got a triangle inside of a semicircle. So it's a triangle made with the diameter, which means that this angle up here is 90 degrees. But we're being asked in this question, so it tells us that the A, B, and C are points on the circumference with the centre O. It tells us that AOB is the diameter of the circle, and we've got to prove that there is a right angle up here. You must not use any circle theorems in your proof, otherwise it would just be a circular argument. So we need to show somehow that this angle is 90 degrees. Now the way I'm going to start this is I'm going to very badly join up these lines here. So join up the centre to C. And the reason that I'm going to do this is because that is radiuses. Both of those are a radius to the circle, which means that this distance here is the same as this distance here. And what we have is an isosceles triangle. Okay, so I can use that with angle rules in order to prove that my triangles that this angle, is a 90-degree angle. So first of all, I'm just going to start off by labelling this X. Now, if I was given this in a GCSE exam and I was sat there wondering where on earth to start, I would get a pencil and start marking something on the drawing. So I know also this one is X. And if that is X and that is X, then this angle is 180 minus 2x. So we need to get that down now. That's a good starting point. So we need to start writing down our proof. So I'm going to start by saying that I'm labelling OAC. So this is my angle OAC, which is OAC. And I'm going to call that one X. And on top of that then, the angle OCA or ACO is also X. And I'm going to state my reasons for this. So these questions, these proof questions, they need reasons. And by reasons, I mean the rules. So what is my rule? It's that base angles in an isosceles triangle are equal. Okay, so there's my first rule that I've used. My giving reasons is giving a rule. Okay, and then what else did I do? I've given this some information now, so let's put that into writing. So angle AOC is equal to 180 minus those two x's. And what's my reason for that? Angles in a triangle add to 180 degrees. Okay, so where am I going with this? Well, now I've done that, let's see what else I can work out. So, working here, can I work out what this angle is? Well, yeah, because that's got to be 2x. We know that these two angles here, this is a straight line, the diameter is a straight line. We know they've got to add up to 180. Well, if this is 180 and minus 2x, then that's got to be the 2x to build up to 180. So let's write that down as well. So angle COB or BOC, whichever way you want to write it, is equal to 2x, and the reason for that is angles on a straight line. Straight line add to 180 degrees. So I'm stating my rule each time. Now, what does that mean for the rest of this triangle? So we go back to the remaining angles here. So I'm looking to find this one to prove that these two add up to 90. And again, what we've got is isosceles triangle here, haven't we? We've got a radius and a radius. So angle OCB, that's the one we're concentrating on now. Angle OCB. Well, how am I going to get that? So these two angles here are 180 minus 2x, and that's the both of them together. So angle OCB is equal to 180 minus 2x, but that is for both of them, so I'm going to divide that by 2. Okay, that then gives me this top angle up here. So now I've got this angle here. Let's just simplify what I've written there. So we can divide, this is take away. So unless I can divide both of them by 2, I won't be able to do it. Now 180 can be divided by 2 and 2 minus 2 can be divided by 2. Both parts of the top of the fraction have to be able to be divided by 2. So 180 divided by 2 is 90, minus 2 divided by 2 is minus 1, or in this case, just x minus x. Okay, and it's the same rule as above. So this is the base angles in an isosceles. Are equal, and really we don't really need to write it the second time, we're just covering our bases. You could also add on to the bottom of that angles in a triangle sum to 180 as well. So now the final bit of our proof we've got here. So we've got angle ACB is equal then to the angle ACO plus angle OCB, which is x and and angle OCB, which is 90 minus x. Simplify that, we've got x, take away x, which means we are just left with 90 degrees, and we have now proven that we have an angle of 90 degrees. Okay, so let's move on to the next slide. Okay, so here we are with our mark scheme. So we've got the proof was drawing OCs and considers angles in an isosceles triangle. So that's what we did at the start, where we joined the centre and we joined that to the angle at the top, that giving us the isosceles triangle. It says then we can use something like algebraic notation to be used, or you can just write that about this. You don't have to give them letters. I just think it's easier to see. So find the sum of angles in a triangle ABC. So however you wanted to label them, which is the one we did, I just stuck with X, so I didn't have to be changing between X's and Y's. And a complete method leading to ACB equals 90. So it says the final bit is a complete proof with all reasons given, and here are the reasons. We've got the base angles of an isosceles triangle are equal, angles in a triangle add up to 180, angles on a straight line add up to 180. And can I just point out that the reason that these six, isosceles triangle, angles and line, those ones are highlighted within this purely because they have to be seen. If you don't say angles in a triangle add up to 180, you won't get the mark for that. So if you said triangles add up to 180, you're not going to get the marks. Okay, it's just something to bear in mind. Okay, so here we have another proof question. So we've got prove algebraically that the straight line with the equation x minus 2y equals 10 is a tangent to the circle with the equation x squared plus y squared equals 20. Now, your brain's going to go one or two ways with this kind of question. It's going to go for, you've got a circle graph, you're going to prove it's a tangent by showing that the gradients are perpendicular. However, we've got no points, so we've not been given any point on these two lines. So that's going to be very, very difficult unless we find a point on the line. Now, the other way to prove this would be a tangent. What do we know about a tangent? Well, a tangent is something that when we're talking about a tangent to a circle, if this is the edge of my circle, it's going to come in, it's going to touch one point on the circle, and it's a straight line. Line's not very straight, but it's a straight line. That means it only ever has one point of intersection. So there should, if I solve these equations, only be one solution to the equations. One point where they both have the same coordinates. So I'm going to need to, because this is a quadratic, I'm not just going to be able to solve them by the usual methods when I've got two linear equations. The easiest way to do this is to take this equation and rearrange it. So I've either got x equals or y equals and swap that into whichever variable I'm replacing. So easiest one is if I'm starting with x minus 2y equals 10, I'm going to go then to just move the 2y across. So x equals 10 plus 2y. Now then, let's substitute that into my equation. So I've got x squared plus y squared equals, oops, sorry, switched into a highlighter there, equals 20. Okay, so I'm swapping my x in, so I should have 10 plus 2y all squared plus a y squared equal to 20. So let's get rid of my brackets. These are double brackets, not single brackets. Plus a y squared equals 20. I keep this all together just so that I'm not going to forget to add it back in. I'm not going to miss anything. There's going to be a lot of variables here and I don't want to lose something by just expanding my brackets elsewhere. So let's expand my brackets. So starting with 10 times 10, we've got 100. Then we're doing 10 times 2y is 20y. And then going the other way, 2y times 10 is another 20y. And finally, 2y times 2y, well 2 times 2 is 4, y times y is y squared, plus another y squared is equal to 20. So this is the y squared from here. This y squared is this y squared, so I haven't just added one from nowhere. Right, let's simplify. So starting with my quadratic portion here, so these two here, the y squareds, let's put those together. I've got a 4y squared and a 5y, another y squared to give me 5y squared. Now then, my y's, 20y and 20y is giving me 40y, and we've got 100 equal to 20. If I'm going to solve an equation, the final bit of this is I've got to have a 0 on this side of my equation. And so let's bring my 20 across, 5y squared plus 40y plus 80, so 100 minus 20. And at this point, to make my life easier, I'm going to divide all of this equation by 5. So y squared plus 8y plus 16 is equal to 0. So looking at this, I can now factorise it. I could use the quadratic equation. I could have put the original one back into a quadratic equation, but I'm going to have a look at solving my equation here. So if I pop it over here, so solve y squared plus 8y plus 16 equals 0. So we're going to look for something that multiplies to make 16 but adds to make 8. So 16, 1 times 16, 2 times 8, 4 times 4. So it's going to be this one, isn't it? 4 and 4. Okay. Now let's pop this into brackets then. Y, and both of these are going to be 4. Everything's positive, so it's plus 4 equals 0. So now the last bit is to look at the solutions then. So solving this one, we know that one of these brackets has got to be equal to 0. So y, because we're multiplying them together to equal 0, it means that one of the factors is 0. So y plus 4 equals 0. It must mean that in that case, y is minus 4. And it's exactly the same bracket here. Oops, minus 4. And my final conclusion, my actual proof of this is what we were saying before, as a tangent is only going to have one point of intersection with a circle. these are the same coordinate, there is only one point of intersection. So that will be my conclusion. Only one point of intersection. So x minus 2y equals 10 is a tangent, and I have just justified my answer. Okay, so looking here then at my mark scheme, my first mark starts the process to find the point of intersection by substituting. So that's taking the linear equation, rearranging it, and either swapping it for x or y in the circle equation. The next one was for expanding your brackets. So this bracket's here, or if you substituted in for the y, so expanding those correctly, and as long as you got 3 out of 4 terms correct, you would have got 2 marks. The rest of this now is dependent on other marks being awarded. If you didn't get mark 2, you can't get the 3rd mark. So if you needed to first of all get this correct, and then to get a 3-term quadratic equation ready for solving. So you've simplified a quadratic down so that you can solve it. So something equal to 0. The 4th mark is dependent on you having done the substitution process in the first place, and is for a method to solve the equation either by factorisation or using the quadratic formula. The final mark is for a fully correct method that leads to either y equals minus 4 or x equals 2, depending on which of the formulas you replaced, so whether you replaced y or x. Or showing that y plus 4 all squared is equal to 0, and then some sort of statement that says only one point of intersection, so the line is a tangent to the circle. Okay, proof is one of those topics that is generally not brilliantly done, so I hope that helped to show you how you might go about some quite tricky ones. Okay, see you soon for some more tricky grade 9 GCSE questions.